Hello, and welcome to this first video in the resistance welding playlist on this YouTube channel, the Weld Nugget. To begin with, let me start by sharing the screen so that you can follow the PowerPoint as we go along. My name is Girish Kelkar, and I am a welding consultant working as WJM Technologies, which stands for Welding and Joining of Materials. In this video, we're going to talk about fundamentals of resistance welding, trying to understand exactly what happens at the weld when the current is passing through the parts which we are trying to weld. Resistance welding is also known as spot welding, since it is most commonly used to make spot welds. That means individual welds at individual locations. Other processes such as laser welding, ultrasonic welding, arc welding can also be used to make spot welds, but not so commonly in all cases. So sometimes it can be a bit misleading when somebody says spot welding. You have to get a clarification if they mean resistance spot welding. Resistance welding, as the name implies, it depends on current flow to form the welding heat. So what we are doing is we are putting the parts together, applying electrodes from both sides, and passing current through the stack to generate heat to make a weld. You can distinguish resistance welding into two categories, small-scale resistance welding and large-scale resistance welding. In small-scale welding, we are looking at making devices which are quite small that you can work on a lab bench and have a tray full of parts right next to you. Oftentimes, small-scale welding is done with a microscope, so the parts are so small. Applications include medical devices, light bulbs, sensors, relays, batteries, solar cells, and so on. Current is typically in the range of 25 amps to 5,000 amps, although in most cases it is in the range of, say, around 100 amps to 1,000 amps. There's another set of industry which caters to large-scale welding, which is automotive and aerospace, primarily looking at structural welds, where we are welding sheet metal, flash welding, and large-scale projection welding, where the current can be of the order of 5,000 amps to 50,000 amps, sometimes up to 100,000 amps, but that's very rare. In most cases, the welds are of the order of, say, 10,000 amps to 25,000 amps. I'm showing you pictures on the left and right of typical scale to give you an idea how big these units are. On the left-hand side, we can see a small-scale welding setup where you can see the weld head. This person is sitting in front of the machine. The weld head is about maybe 1.5 feet tall. And the power supply to the right is supplying the energy, and that is about the size of a microwave oven. In contrast, large-scale welding, where we are talking about currents of the order of 25, 30,000 amps, we can see most of these machines are mounted on the floor. And if you can compare to the person standing over here, this machine itself from the floor to the top is about 10 feet tall. So obviously the scale is different, but the fundamentals remain the same. A lot of the large-scale welding is also done with robots for car body welding, which you may have seen videos on when you watch some news items. But again, the fundamentals remain the same. Let's look at the fundamentals of how the heat is generated, where it is generated, and what is the result that it produces. Here I'm showing you a schematic of two electrodes, one on top, on the bottom. They're shown red in color, as typically electrodes are copper, but again, not necessarily. They can be molybdenum and tungsten and so on. And the two parts being welded are shown gray in color to signify steel, but here again, the parts themselves can be copper, silver, gold, inconel, titanium, and so on. I'm showing you schematically a circuit where the current is forcing the current to go through the electrodes, through the parts, and come back. What is interesting to note that in resistance welding, when we think of generating heat and in a resistance, we think of I square RT, the equation for heat generation. where we think of only one resistance. However, in resistance welding, we have to deal with 7 different resistances, and they are dynamic, and that's what makes life challenging in resistance welding. So let's look at these resistances. We have first look at bulk resistance, that is the resistance to current flow inside the part. So as the current flows through the electrode, it encounters resistance R1, then it flows through the top part, this bottom part, and into the bottom electrode, and the resistances are R1, R3, R5, and R7. Now, these are bulk resistances. That's a resistance to current flow inside the part. There are also 3 contact resistances. That is the resistance to current flow as the current jumps from one part to the other. In this particular case, going from electrode to the top component or top part, we have the contact resistance R2. Then between the 2 parts we are trying to weld is R4. And as the current jumps from the bottom part to the bottom electrode, we have the resistance R6. Ideally, you want to generate the maximum amount of heat at this interface because that's where you want to make the weld, right where R4 is. But let's see what actually happens in real life as these resistances change over time. So let's see, first of all, how contact resistance changes over time. Contact resistance, I've shown schematically over here. There is contact resistance on the vertical axis and force. On the horizontal axis, we are looking at time. As the 2 parts come together, at the beginning, the parts are actually microscopically quite rough. So the contact resistance is actually very high. As force is applied to pull the parts together into intimate contact, the contact resistance drops quite quickly. At the beginning of the electrical cycle, as current starts to flow, the current will initially flow through these high points, and these high points become soft. And as we are continuously applying the welding force, the high points start to collapse. And pretty soon, both the parts are in intimate contact at an atomic level, where the contact resistance goes pretty much to 0, assuming there is not significant oxides on the surface. So the contact resistance has gone from being very high, brought down by initial pressure, and then brought down by initial flow of current. It goes down to 0. On the other hand, bulk resistance is the resistance to current flow inside the part. Bulk resistance, on the other hand, increases with temperature. So the bulk resistance value, whatever it is at room temperature, by the time you get to the point where the material is almost close to melting, the bulk resistance is of the order of 10 times. However, the contact resistance actually changes by many orders of magnitude. So here we have the dynamic. The contact resistance is very high, it goes down, the bulk resistance is low, and it creeps up towards the end of the cycle. Let's see what it looks like in a schematic form. Here we are again showing resistance on the vertical axis and time on the horizontal axis. We have the contact resistance shown by this dashed green line is very high in the beginning, and it comes down rapidly and at some point almost goes close to 0. On the other hand, the bulk resistance shown in this teal color starts low and slowly goes up towards the end of the weld. How can we make use of this dynamic change in resistance to benefit our expectation from the weld? Here I'm showing you a schematic on the left-hand side, where again, showing you the same schematic where the contact resistance goes down and the bulk resistance goes up. But in addition to that, I'm showing a schematic where we are sending a short but high pulse of energy early on in the weld. So right where the contact resistance is still very high, we send a sharp pulse of energy to create the heat. The effect of that is a lot of the heat is generated at the contact interfaces. And what we will see is the heat affected zone, or sometimes even the fusion zone, extends all the way from the top surface to the bottom surface. Another interesting feature that might show up in some of these welds is the formation of a porosity in the middle of the weld. This porosity is not from contamination, but this is from rapid expansion of the metal, and the metal freezes at the end of the cycle before it can come back. So it's a telltale sign of a short cycle weld. On the other hand, we can make another weld which looks very different, where we allow the bulk resistance to dominate. How do we do that? We start slow, we gradually increase the current, and then we send the current for an extended period of time before we turning it off. What that does is it allows the contact resistance to go down very quickly, and now all the heating is primarily governed by the bulk resistance. Plus, because the heating is a little bit slower, it allows the electrodes themselves to actually remove some of the heat from the two surfaces and controls the size and shape of the weld nugget. Now, these I'm showing you in schematic form. Let's see what it actually looks like in a real cross-section. Here I'm showing you a comparison between the two. Here on the left-hand side is what a cross-section would look like in a typical short cycle weld under certain circumstances. On the other hand, on the right, I'm showing you a weld, what is typically looks like from a long cycle weld. Again, these are representative ones. There are always some extremes where the appearance can be quite different. In the short cycle weld, we notice that the heat affected zone has extended all the way from the top surface to the bottom surface. We can actually see a fusion nugget over here if you look closely, which is also extending pretty much all the way to the surfaces. Because the entire thickness of the welding stack has become so soft, what happens is the welding force applied by the electrodes causes then an indent on the surfaces. So we can see an indent on the top surface, an indent on the bottom surface. And we are also seeing a porosity in the middle of the weld. Now, this porosity is from rapid heating and cooling, and it is not from contamination. Why would we be interested in making a short cycle weld? A short cycle weld is useful when we are welding conductive alloys. In conductive alloys, such as if you're welding copper or silver or gold, the alloys themselves don't have a lot of resistance. So it is difficult to generate heat in a long cycle weld because the bulk resistance of these alloys is very low. So our best bet is to use the contact resistance. So that means we have to send a sharp spike of energy very, very quick early on to generate the heat at the interfaces. On the other hand, the long cycle weld, which is ideal for resistive materials such as steel, stainless steels, Inconels, titanium alloys, and so on, that can produce a weld nugget which is completely contained inside, and yet there is almost no effect of that weld from the outside. Because it's a long cycle weld, it allows the electrodes to conduct the heat away from the surfaces and maintain a fairly much lower temperature close to the surface, which is in contact with the electrodes. The net result is we can produce a markless weld, and we can very carefully control the size and shape of the weld nugget. So this essentially is the fundamental of how the heat is generated, where, in what quantity, in what distribution. So as an engineer, as a designer of this process, you will have to figure out which way you want to go, whether you want to go with a short cycle or a long cycle. And again, there are many other aspects involved in that. There are different materials, different electrodes, different equipment, different expectations. But this is exactly what you need to think about when you are about to set up a resistance welding process. Thank you. This is the fundamentals of resistance welding. You will find other videos on resistance welding in this playlist, which elaborate on different aspects that I just reviewed. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel. So every time I upload a new video, you will be informed. Videos on specific topics are in different playlists on this channel, so feel free to browse through and enjoy the videos. Thanks for looking forward to keeping in touch, and thank you.